All right, so section 5.5, we're going to be looking at exponential functions that have bases other than e, and then also looking at some stuff that is pre-calc topics, but I don't think you got the chance to do them last year, so we'll look at a couple of pre-calc topics here at the beginning. So first of all, half-life. This is, again, a pre-calc thing that I just want to make sure you understand before we go into other things. So half-life of 800 milligram ibuprofen is 1.8 hours. How much ibuprofen is left in your system 4 hours after you took a dose? So your general formula for this, it's like, the amount, this is a function in time. We have our initial amount, okay? The initial amount, which we can label as like a sub 0, like we do initial velocity, we do v sub 0. So there's your initial velocity times the base raised to the time divided by k. Now let's, what do each of these things mean? Well, a sub 0 is your initial amount, okay? So your, initial amount. T is the time. All right, so your time for this one is going to be 4 hours. Your initial amount, we'll just put a 4 there. Your initial amount is how much ibuprofen you took, which is 800, so that'll be 800. And then b and k are related to each other. So b is your base of the exponential function, and k is how long it takes to achieve that base. So what I mean here is we're told half-life, so we're talking about half-life. So for b, in b and k will change there, for every problem. So b is your half-life. This could be like a population doubles every 3 years, then b would be doubling, it would be 2, and k would be 3 years. In this case, b, we're talking about half-life. So this is your half-life, so that's going to be 1/2. And then k is how long does it take for it to get to that point, which we're told it's 1.8 hours. So let's kind of fill this in here. We're going to do this again for 12 hours, but let me move that down. I didn't give myself enough space. So we're going to do this for 4 hours first. Now, if you look at the bottle of like Advil, you'll see on there it says to take it, however many milligrams every 4 hours. That's typically your dosage time period that you wait to take another dose. So we're going to start with 800. Talking about half-life, so our base here is 1/2. And just as a general function, we can have t divided by 1.8. Okay, because if we plug 1.8 in for t, that will give us an exponent of 1. 1/2 to the first power would be 1/2 times 800 would get us down to our 400 milligrams, which would be our, that's the half-life. It's how long it takes for it to have half the amount left in it. So now what we're going to do next is we're going to plug in 4 because we want to know how much will be left after 4 minutes. I'm sorry, 4 hours. So 1/2, we're going to raise this to the 4 divided by 1.8. All right, so let's break out our calculators and we will plug this in and see what we get. Now, we know that we should be less than 400. And really, if we look at this, if that was, instead of 1.8, if we had 2, it would be doubled. So we really should be somewhere in the area of 200. So plug that in, 800 times 1/2, which you could just enter 0.5. Raised to the, when you do your exponent, I would divide, or I would put parentheses there, just to be safe. And what you should get, what I just got here when I plugged that in, was I got approximately 171.449 milligrams. Okay, so technically, if you take 800 milligrams every 4 hours, at the end of the 4 hours, you still have about 171.5 milligrams which is basically like one pill, because each pill is about 200 milligrams of a normal Advil. You have about that much left. Okay, so my next question is, how much is left after 12 hours? So we're going to take that same function and we're just going to plug a 12 in for t. So 800 times 1/2. Now we have 12 over 1.8. And what do we get here? So I'm just going to scroll back through my function that I already have entered. And I'm going to do 1 and then insert the 0.2. Yeah, 0.2. Or not 0.2, I'm sorry. 12. And you can see that it has reduced significantly. After 12 hours, we are down to, let me make sure I entered that right. Yep, 7.875 milligrams left. Okay, now that's, again, assuming we haven't taken more doses later on. Okay, so again, that's half-life. That's something that you would typically cover in pre-calc. I have no idea if you guys covered that last year or not. So I just wanted to go over that a little bit there to talk about that. So change of base formula is another concept that you learn in pre-calc. Now, what's the purpose in doing this? Well, basically, our calculators have base 10 and base e built into them. And because our integrals and derivatives for base e, the natural logarithm, are much easier, a lot of times we're going to use the change of base formula, and we're going to change that to ln. Now, you could change that to any base you wanted to. Okay, we could start with a log base 5 of 20, and we could change this to a log base 10. We could change it to log base 2. We can change it to log base e, which is what we want to stick with. We want to always change to log base e. And like I said before, the reason for that is because our derivatives and integrals are much simpler for a natural logarithm. So there's your change of base formula. Okay. And let's look at some other examples here. Again, we went over some examples of solving exponential and logarithms using, just like the concept that you did in pre-calc. But sometimes we can do this and get an exact answer. This is when we could get an exact answer. So you have two options. I'll start this two different ways. The way that we did it the other day was we wanted to take, if we want to bring the exponent out, we have to take a log of both sides. So we could do ln of 3 to the x equals ln of 1 over 243. Okay, so that allows us to bring that exponent out front. So we would have x ln of 3 equals ln of 1 divided by 243. And then to solve for x, we would divide ln of 3 over, and we would have ln of 1 over 243 divided by ln of 3. And that you could plug into your calculator. Okay, you can just plug ln of 1 divided by 243 and divide that by ln of 3, and your calculator will give you -5 for the answer. So I don't know if this is something you guys covered in pre-calc or not, but this answer here is -5. Well, how do we get that? Basically, if we can rewrite this as 3 to some power, then if they both have a base of 3, we can set the exponents equal to each other. So first of all, if I move the 243 up, I have 243 raised to the -1st power. Now, I want to try to write this as 3 to some power. Okay, so if we run through our exponents of 3, we have 3 to the 1st power is 3, squared is 9, 3 to the 3rd power is 27, 3 to the 4th power would be 81, and then 3 to the 5th power gives you 243. So we can write that as 3 to the 5th power raised to the -1st. So basically what we're left with here now is 3 to the x power is equal to 3 to the -5th power, because we just multiply these two. If your bases are the same, then we can get rid of them, we can cancel them, and just say x equals -5. Alright, so there's two ways of doing the exact same problem. If you did this in pre-calc, you probably covered it using that method right there on the right-hand side. How about a logarithm? Again, we talked about this yesterday when I mentioned the triangle of death, and we say this base 2 raised to this power 4, negative 4, equals this right here, which is x. And then we just use some algebra 1 exponent rule stuff. The negative moves it down. So 1 over 2 to the 4th equals x. And then we do 2 to the 4th power, which gives us 16. So we end up with 1 over 16 as our final answer. Okay? All right, so let's look at some calculus stuff now. So go ahead and pause this, write it down, and then I'll talk about some of them. Okay, so we talked about 1 and 2 when we did the logarithm stuff. Okay, if we have ln, if the base is e, then it's just 1 over x. But anytime we change the base and we use some other base other than e, this is our derivative. We still have the 1 over x, but then also in the denominator we have ln of whatever your base is, okay, which we're using the variable a for this. Same thing if we're dealing with chain rule, 1 over u, ln of a, and then the derivative of u, whatever that may be. When we do the derivative of an exponential, now like I told you, we went over yesterday, if the base is e, if we have e to the x, then we just have e to the x. But also what's in here that we don't write is we do have an ln of e. Okay, but ln of e is just 1, so we don't write that and we just say it's e to the x. So you can see that that's here in your formula. Whenever the base is something other than e, we actually have to write that because it doesn't just give us 1 now. Okay, and this says when a is not equal to 1. Well, why does it say that? Because right here, ln of 1 would give you 0, so this whole derivative would just be 0. Okay, so that's why we don't do that. And you can look at the graph of 1 to the x power, and if we have 1 raised to the power of x, this is just equal to 1, which is a constant, which is why the derivative gives you 0. Okay, so there's a little bit of information on that one. And again, when we deal with chain rule, a to the u, if your exponent is something other than just a straightforward x, we just copy that down. We do ln of the base and then the derivative of the inside function. Okay, so nothing new there for chain rule, just a new function with our exponentials here. So yeah, let's look at some examples now. Oh, got the same slide on there twice somehow. Next one, here we go. Find the derivative of each function. So first up, y equals 2 to the x. So if we're doing y prime, again, we always recopy 2 to the x. If the base is something other than e, we need to do ln of that base, so ln of 2. Okay, and I mean, you could have absolute values, but 2 is already positive, so we don't need to do that. Okay, so that would be your final answer. You could rewrite the ln out front because this is a constant. We could do that, but what I don't want you to do is accidentally put ln of 2 times 2x and then write ln of 4 to the x or something like that. So we just leave it like that. That's fine. And then this one, again, we have an exponential function, so the derivative always just recopy. And then we're going to do times ln of the base because the base is not e, so ln of the base, which is 10. Since our exponent was not just simply an x, we need to multiply that now by the derivative. So the derivative of 5x is just 5. There are multiple ways that you could write this. 10 to the 5x, we can't write that any other way. But we could write this as 5 ln of 10. And then from your exponent rules, logarithm rules, this could be ln of, we can move this up to the exponent. So that would be ln of 10,000. No, I'm sorry, more than that. 1, 2, 3, 100,000. I missed a 0 in there in my notes. 100,000 because we would have 5 zeros. Okay, those are all three the same thing. So yeah, just keep that in mind that you could have multiple ways of writing your derivative. But again, you're looking at your multiple choice answers and you're seeing which one is the correct answer. When we do, we got one more of these. So y prime, take the derivative. Now we have a logarithm with a different base. But again, we're always starting out by just doing 1 over the inside, which is cosine x. Also in the denominator, we have times ln of the base, if the base is not e, which the base right here is a 10 if it's not written. And then we multiply by the derivative of the inside. Okay, so the derivative of cosine is negative sine x. So clean this up a little bit. I do have sine over cosine, negative sine over cosine actually. So what's negative sine over cosine? Well, that's negative tangent x, and your denominator is ln of 10. So that is most likely how you would see your answer written on the AP test. All right, now looking at integrals with bases other than e. So if we, like we talked about before, if we had the integral of e to the x dx, this was just equal to e to the x plus a constant. Now if the base is something other than e, we have this part in here again, the ln of the whatever the base is on the denominator. So like this one here, integral of 6 to the x dx. Again, we recopy 6 to the x, but now we're going to multiply this by 1 over ln of the base, which in this problem is 6. No numbers on your integral means we need to have a plus c, and this would most likely be written as 6 to the x power over ln 6 plus c. So that's most likely how you would see your answer written. Now what I want to do is just kind of wrap up this section here with these derivatives, looking at 4 separate derivatives. There's 4 different ways that we do these problems, so let's just talk about them. So go ahead and write those down and then we'll see what we get. Alright, now first up, e raised to the power of e. This right here, e raised to the power of e, since e is a constant that's approximately 2.71, this is basically like saying 2.71 raised to the 2.71. E raised to the power of e would be the same thing, it's the same concept as pi raised to the power of pi. Either way you look at that, this e raised to the e power is a constant. We take the derivative of a constant and we end up with 0. Okay, so just keep that in mind. E is a number, so if we have a number raised to a power of a number, it's just the same thing if we had like 5 raised to the 5th power. Okay, we don't bring the 5 down and then subtract it by 1 and do that. We don't do that. This is a constant, and the derivative of a constant is always 0. Okay, constants can take on many forms, and sometimes they take on the form of a letter, not a variable. E is not a variable, it's a letter that represents, approximately 2.71, blah, 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 blah. The derivative of e to the x, this is e to the x. We talked about that yesterday. X to the power of e, again, may look confusing, but remember, e is a number. So if we have x raised to the power of 2, what do? Well, we bring the power down, and we subtract it by 1, and we have 2x to the 1st power. So bring the power down, and then we have x raised to the e minus 1. Okay? And that's how you would write your answer. X raised to the power of x. What happens if we have a variable raised to the power of a variable? Well, this is when we did our logarithmic differentiation that we did the other day. We take a log of both sides, mainly ln. So ln of y is equal to ln of x raised to the power of x. This allows us to bring the exponent down, so we'd have ln of y equals x ln x. And then we would take our derivative. Okay, and we'd say derivative of ln y would be 1 over y times, chain rule, implicit diff, y prime, equals product rule. The derivative of the first is 1 times the second, plus the first times the derivative of the second would be 1 over x. So we would end up with y prime equals, multiply the y over, and then we have ln x plus x over x is just 1, And then we would replace the y with what we knew about it. So y prime would be x raised to the power of x times ln of x plus 1. Okay, so again, that's logarithmic differentiation. We did that earlier in the chapter, and that's how you would handle that problem. Okay, so like I said, 4 different ways to view e's and x's, and I just wanted to make sure that you can, differentiate the difference, or I shouldn't use that word. You could tell the difference between them and know which derivative you do, when do we do them, how do we do them, what do they look like in their different forms. So here's some problems for you to try. And again, like always, if you have questions or anything, just let me know. If you have any questions on the problems, I can go over them and send you a video of that. Or you can send me an email or a private comment and just let me know what questions you have.